Oh, all right, folks. So welcome back. I guess today I can correctly wish you a happy Friday. I apologize about yesterday. I think it was like I pointed out in the my note for the lecture yesterday. I think it was more wishful thinking on my part. But today is Friday, so happy Friday, folks. And I hopefully we will look forward to a pretty nice weekend this weekend where we can probably try to get out a little bit. Hopefully and get some of the uh, fresh air from outside. Okay, but hopefully you're able to watch the video and answer the question that I left you with, and that is, we were talking about liquids, and we were talking about how with liquids, and so let's go ahead and quickly recap where we left off with yesterday, and that is we said that liquids have certain properties that we're going to talk about. We're going to talk about evaporation today, and I asked you about that yesterday. We're going to talk about boiling point, and we'll talk about that. We'll talk about vapor pressure as well. Um, so liquids as a state of all liquids. So the liquid state has certain properties about them that can be described at the molecular, at the atomic level. We saw then how with how a liquid we're able to describe then how liquids are able to assume the shape of their container, and we saw then how liquids were also, unlike gases, are able to maintain their own volume. So we were able to explain, just like we were able to explain gas pressure on a molecular and atomic level, we were able to obtain explain those two properties of liquids on an atomic and molecular level as well. Okay, so let's go ahead and recap real quickly how we were able to explain, for example, why liquids have no shape of their own. Well, we said that liquid particles move. Okay, we said then that liquid particles have this ability to move in much the same way that gas particles have ability to move. So let's go ahead and let's make sure you understand that. Okay? So let's consider then a liquid particle here. So we'll look at liquids first, and then we'll use this to recap before we start talking about um, um, evaporation. Okay. So liquid particles, they don't sit in one place. They don't sit in one place according to the kinetic molecular theory, which we opened this chapter talking about. Okay, all particles are all in constant motion. Okay, and so these liquid particles they move. They move in a random and in a rapid manner. Okay, in much the same way that gas particles move in a random, rapid manner. So this motion that they have then is what we refer to as translational motion. Okay, which means then that these particles they start out at position. So let's say then that this is the start. This is the starting position. So they start out here and they end up somewhere else and they end up at a different position. So this is the start position and this is the ending position. This type of motion here is what we refer to as translational motion. That means then an object picks itself up and it moves. It just doesn't move in one place. And so these liquid particles, what they do then is they pick themselves up and then they move from one point to another point. They start out at one point and they end up at another point. This translational motion here allows us to explain then, and this is the reason why we can explain then that liquid particles flow. Okay? Because of this translational motion, liquid particles flow, and because of this flowing nature of liquids, liquids then are able to move around. Okay, so we can talk about liquid flowing both on a microscopic level here and on a macroscopic level. If you take water here and you pour it out, it will move from one position to another. If you take this water here and it's flow and you put it at this end at a higher point and this end at a low point, the water then will start to move from high to low point. It will change its position from the start to the end, very much in the same way that the rivers flow from one point to another. So the flowing nature of liquids can be seen, we can observe that on a macroscopic level, but we can also explain it on a microscopic level here where these particles are moving from one position to another. And as such, because of this flowing nature of liquids, okay, they will assume the shape of their container, which means then they have indefinite shape. And because of that, we can say then that liquids have indefinite shape, and that's how we were able to explain this particular property of liquids. Now, the difference between liquids and gases, and let me just go ahead and draw the gas particles in here really quickly. Okay, so let's imagine that there are gas particles floating around, because we know they are. The difference between gas particles, because remember, we said gas particles also flow. They also assume the shape of their container. Gases have indefinite shape as well. Okay, the key difference in the way they move, gas particles just move a whole lot faster. They also have translational motion. And so we can represent this motion of gases, okay, by drawing arrows that are much, much longer than that of a liquid. Meaning then the gas particles here can move from one point to another much faster than the liquid particles do. But they both move. They both have this translational motion here as well. So that's why both liquids and gases flow, and that's why both liquids and gases assume the shape of their container. Okay, so that's what we left off. So that's what we talked about yesterday. Okay, we talked about then how this is how what liquids and gases have in common. Okay, so let's continue to compare liquids versus gases. Okay, so that's what liquids and gases have in common. Okay, let's continue with this comparison, and then and so we were able then to explain how liquids have some other second property of liquids, and that is liquids have definite volume. Okay, so even though they have indefinite shape, okay, liquids have what we call definite volume. Okay, so let's go ahead and let's take a look at the liquids, okay, and why they have this definite volume. So as liquid particles move around, okay, so we said that as these liquid particles move around, what they do then, okay, is that they have what are called these attractions for another. That means that as they move around, they are tethered, or they are stuck. You can imagine this, okay, to every other particle around them. If you can imagine, these green dashed lines represents these attractions. They hold on to each other, meaning that as they move around, they also hold on to one another. Okay, so these attractions here, they keep the gas particles together. I'm sorry, they keep the liquid particles together. They keep them together. So you can imagine then that they are kind of tethered together as they move around. So as these liquid particles move around, and they are in, remember, constant motion, as they move around, they are tethered to every other particle around them. Okay, so they basically are trying to hold each other in place, but they can't because they're moving so quickly. They're trying to move to hold each other in place, but they're unable to do so. And so because of these attractions here, and that's what I want to make sure I remind everyone of, because of these attractions here, okay, because of these attractions here, we have then these interactions, these attractions here. We have then these particles sticking together, and because of that, we can explain then that they basically will occupy a set space. That means they're not free to just move wherever they want to. Yes, they move. Yes, they move around. They have this translational motion, but the range of that motion then is going to be limited. Okay, so these attractions here, the forces the liquid particles to limit the range of motion. Okay, so these attractions here limit the range of motion. Okay. So they limit the range of motion, and as a result, these liquid particles occupy a set space. So the liquids occupy a set space, which means then, we talked about this, they will have then a definite volume. Okay. So gas particles, on the other hand, as they move around, so let's go ahead and draw our gas particles. Gas particles, as they move around, and we talked about this, okay, as they move around, they also move in a translation manner, but they move at such a high rate of speed, even though they're, and so again, I want to make sure you understand this. these attractions don't go away. Remember, we talked about these attractions as being those intermolecular forces. These attractions being these intermolecular forces, they don't go away. It's just these gas particles are moving at such a high speed. They're moving so quick. These interactions, these attractions here, basically, and this is what we actually assume when we start talking about the gas laws, they go away. That these attractions here are not strong enough to hold these gas particles in place. So these gas particles then do not occupy a set space, and so therefore they have an indefinite volume. Okay, and so when we go about comparing liquids to gases in this manner, liquids and gases have certain properties in common, um, and they are different as well. Both of these are what we call, both the liquid and the gas state are what we call fluid. These are the fluid states because they flow. However, there's a key difference between how they flow, and that is how fast they move, how fast they undergo this motion. Okay, so with that said, then please make sure you keep that in mind, because that's what we're going to do as we move forward. As we move forward here, okay, you have to make sure you keep. Oh, sorry, folks. Hold on a second here. All right, let me go ahead and get that out of the way. Okay, so as we move forward, what you need to make sure you keep in mind then is that the motion of the gas particles, the motion of the gas particles and these attractions. So as we move forward, folks, and I want to highlight this to you, the explanation that we will be able to give for the other properties of liquids that we're going to talk about, evaporation, vapor pressure in this moment, is going to be based upon the balance between motion, okay, and these attractions. Okay. Okay. So gas particles move, but they also attract one another. Okay. This is what makes gas particles so unique in terms of the three states, because this is what makes the liquid particles so unique in terms of the three states. I mean, yes, they sit between the gases and the liquids, but gases and the solids, but they also share common properties with both gases and solids as well. So with liquids then, we need to keep in mind then that liquids move, but they also attract one another. Okay, and so this motion here, make sure you keep this in mind. This is going to be what we call the translational motion, and that's going to help us understand and explain then the properties that we're going to talk about moving forward, starting with then evaporation. Okay, all right, so let's get out your paper from yesterday, and I asked you to try to explain evaporation on a microscopic level. Okay, and then we can use that to discuss it. Okay, so hopefully, so go get your paper, pause the video, go get your paper, and let's talk about let's compare what you came up with what we're going to talk about here. Okay, all right. So first of all, let's go ahead and let's quickly describe what evaporation is, what this process is. Okay. Well, first of all, we know then that water, when it's left out in the open, okay, when we do nothing to it, whether it's on a desert here or we have it sitting out on our countertop, okay, water, if it's just left out in the open, will eventually disappear. Okay. This disappearing is basically what we refer to as the vaporization of the water. And what's happening here is that it disappears not because it's gone. It's not some magical process by which it disappears. But what we're going to see here then is that the water particles, so if you can imagine the water particles sitting on the surface here, okay, the water particles sitting on the surface, they are moving around in a random, rapid manner. Okay, so these liquid particles, this is the liquid now, so these liquid particles sitting inside the water here, okay, it becomes a gas state. So vaporization is the process by which the liquid becomes a gas. And so that's why with water, when it's left out in the open, okay, and again, regardless of where you're at, left in the open, the water will eventually disappear because it vaporizes. It becomes a gas, okay? And so this process of vaporization, okay, when it occurs, again, when we leave the water just out in the open, when it occurs at roughly atmospheric pressure and roughly the temperature of a room is what we refer to as evaporation. Okay? So evaporation occurs mostly at ambient temperature. Now understand this, okay? Evaporation occurs at all temperatures, and this is what you need to make sure you keep in mind as we move forward. Evaporation occurs at all temperatures. Okay? So we specify evaporation then as the vaporization, that is the conversion of a liquid, okay? Liquid to gas. Okay? Okay. When the liquid is not boiling. Okay? And we'll need to specify what boiling is, but that's how we define evaporation. Now, it'll be easier to understand when we take a look at what happens at the surface, at the particle level here. But the basic definition we're going to give here for evaporation. The evaporation is a process by which a liquid becomes a gas. It is a vaporizing process, but it's a vaporizing process that does not involve boiling. So what we're doing here is we are saying that there is a difference, folks, between evaporation. There's a difference between evaporation versus boiling, and that's why we'll be talking about both of these in turn. So the evaporation is a process that is different for different liquids. Boiling is a process that is different for different liquids. So both of these properties of liquids, the liquids evaporate. Liquids boil. Gases do not evaporate and gases do not boil. Solids do not evaporate and they don't boil either. Okay, so these two properties here, evaporation and boiling, are unique to liquids, okay? But they are not the same. They're not the same, though both involve the liquid to gas transition. So as the liquids transition to gas, this process we call vaporizing, it can either evaporate or it can boil, or and understand this, it does both. It can do both. Okay, so keep in mind as we move forward, there will be a difference between these two, and we'll have to explain those differences, okay, in just a moment. Okay, all right. So that's what evaporation is. Okay? So evaporation is the process by which we vaporize a liquid. Okay, but it's not boiling. Okay, and the key difference between evaporation and boiling will come down to the temperature. Okay, and the properties in different liquids will have different temperatures at which they evaporate and different temperatures at which they boil. Okay, so let's make sure you keep that in mind. Okay, so hopefully you have that. Okay, so that's what we see. That's at the surface. That's at the surface. We see then as that's what we can observe. We can observe on a macroscopic level that as liquids begin to disappear, they are vaporizing. So evaporation is the process by which we vaporize the liquid at a temperature lower than its boiling temperature. Okay? So what's happening here then? Okay? So let's explain this on a microscopic level. Okay, so and explaining on a microscopic level will allow us to clearly differentiate between the process of evaporation and the process of boiling. Okay, so let's make sure you keep in mind then that and that's why I wanted to review this, that there are these interactions. So we refer to these as attractions. These interactions, these attractions between liquid particles. Okay, so remember these liquid particles as they move around. Okay, as they move around, we see it here. I'm sorry, let me go ahead. Really quickly. As they move around here, they are attracted to one another. There are these attractions that holds all of these liquid particles in place. Okay, so they are attracted to every other liquid particle around them. These attractions then, they hold the particles in place. Okay, so these attractions here, these interactions, they hold the liquid particles, they hold the particles in place. They don't allow, essentially, they're trying to keep these particles from moving around. They hold the particles in place. But like I said, the difference between liquids and what makes liquids unique is that they continue to move around. So what happens then is all of these particles at the bottom, they're moving around. All of these particles at the top, they're moving around, and they're moving around in all different directions. Okay. So some of these particles here, if you notice some of these particles here, if they are moving in the correct direction and if they are able to move fast enough here, they will break free of those attractions. So let's take a look at this one here. Imagine this particle here flying off in that direction, okay? Because now it's broken free of all of the attractions around it. And the particle here, which is sitting at the surface, this is a surface particle. And so let's differentiate that. This is sitting at the surfaces, so this is the surface of the liquid, okay? So this is a surface particle, can do what these particles underneath cannot do, and that is to fly up into the, up above, okay? Up into this space above the liquid here, okay? It is that process right there where a where a particle, okay, a gas, the liquid particle mixes with the air above it. That means it flies up into the air above that space above the liquid. Okay, when it flies up above the space, when it flies up to that space above the liquid, it's broken free of the liquid. It's broken free of the liquid, and so that particular liquid particle now has become part, will now become part of the gaseous phase. It has transitioned from a liquid particle to a gas particle. So this liquid particle here, this particle here has become a gas particle. It has become vaporized. Okay, and so that's what we refer to. So some of these gas particles at the some of these liquid particles at the top, they will break free. They will have enough kinetic energy and they will break free. And as soon as they do, and I'm running out of time here, as soon as they do, make sure you keep this in mind, the liquid particle, the particle that was once a liquid particle because it is part of the liquid, becomes now a gas particle. And that is how we can define then this process of vaporization. This is vaporizing. This is the process of vaporization, okay, at the particle level, at the molecular level, at the atomic level. That is, you take a particle that was once part of a liquid. Why was it part of a liquid? Because it had these interactions, it had these attractions to other liquid particles. But as soon as it breaks those attractions and it flies free up into the space above here, it now has become a gas particle. So the liquid particle has transitioned to a gas particle. That is what we refer to as vaporization. Okay? Liquid becoming gas, not only on a macroscopic level, but on a microscopic level too. The liquid particle transitions to this gas particle. Okay? All right, so that is how we can define evaporation on a microscopic level. That's how we can define and observe evaporation on a macroscopic level as well. And so I apologize. I know that we went a little bit longer with the review, but I'm okay with that. Please make sure you take a look at that review today. I won't ask for you to turn anything in, but review and take a look at that, what we did at the very beginning of class today, and look at that, okay? And use that to help you as you move forward, because as you move forward, and we'll talk about this on Monday, okay? We're gonna finish up this discussion of how liquid particles become gas particles, and that's how we can explain evaporation, but that is also how we are going to explain how liquids exert a vapor pressure, and then we'll differentiate towards the end here between evaporation and boiling as well. Okay. All right. So very good, folks. Have a good weekend. And like I said, we'll pick up with this discussion on Monday. There's nothing that I need you to turn in for today's lesson, today's lecture. And so what we'll do is we'll pick up with this discussion on Monday. Okay. All right, folks. Have a good weekend. Okay.